I'm at the old Wattle Gully gold mine in Victoria, southeast Australia. More than 400,000 ounces of gold came up this shaft. And like other orogenic gold deposits, the gold and the quartz were precipitated from a metamorphic fluid. The evidence for this is in the quartz. Tiny samples of the original fluid are preserved as microscopic inclusions. In this sample, the fluid inclusions are over 400 million years old, but they can still be probed and studied. And they can reveal so much about that original ore-forming fluid, its composition, and its likely origin. One of the best researchers in this field has worked at this mine and has studied these fluid inclusions. I went to Australia's capital, Canberra, to catch up with Professor Stephen Cox to learn more about these fluids.
It's quite exciting to go to a microscope and study a sample of one of these veins which host the gold. If you zoom in on a high-power microscope, you see these tiny little fluid inclusions, and in them you can see water, a little bubble of carbon dioxide quite often. That'll be liquid carbon dioxide because it's still at high pressure. And in the middle of the carbon dioxide you'll see a little vapour bubble, which is CO2 vapour, and water, which is just bouncing around in there due to Brownian motion. And sometimes you see little other mineral, daughter minerals in there, sodium carbonates and things like that as well, where the sodium is contained in the fluid.
Just where did these fluids come from?
Finding the source of the fluids is actually a tricky question, a tricky problem. What we usually use is what's the chemistry of the fluids? And what we do know from examining fluid inclusions is that the chemistry of these fluids is dominated by water, so there may be 80-90% water. The rest of it's dominantly carbon dioxide, CO2, sometimes with a little bit of methane, sometimes a little bit of nitrogen, tiny quantities of chloride, sulfide, sulphur, things like that in it. All those things point to the fact that the fluids are probably derived from deeper than the middle of crust, that is deeper than about 15 or so kilometres. We think they could be forming as the crust is being cooked, as you have plate collisions occurring. The rocks are getting hotter, they've got a little bit of structurally bound water in them, so as those minerals get heated up during metamorphism, they gradually sweat off, if you like. The fluid comes out of the crust crystal structures, micas, things like that. The chemistry suggests that there's probably a lower crustal source, possibly a little component of fluid also coming out of the very highest levels of the mantle at depths of maybe 30-40 kilometres.
Yeah. So as these rocks are being metamorphosed, chemical reactions are liberating elements, including gold.
Yes, so the micas, for example, micas or minerals like one called amphibole, as they are cooked up, as they heat up during metamorphism, they change their structures, they change into, or phase transform into new minerals. As they do that, they release water, and as the water leaves that mineral grain, it carries some elements with it, and gold is one of those elements which it'll carry. If it's got enough chlorine in it, it'll carry it, or enough other species, it'll carry the gold, sulphur in it. That fluid then leaves the mineral grain and migrates around grain boundaries, gets into fractures, and then migrates upwards towards the Earth's surface because the pressure drives it that way. Yeah. We can think of the system something like a tributary system in a big river, that we have all these little sources of fluid. The minerals are devolatilizing, they're letting their H2O and their CO2 go. That fluid starts to migrate, it gets into bigger fracture channels and bigger shear zones, ductile fault zones, and continues migrating up towards the crust into bigger and bigger fault zones as it gets higher and higher.
So what about the gold? Where do you think the gold was derived from?
Okay, we may not need a particularly special source. What we know is that the gold content of many rocks is very low. For example, a typical granite or a typical metamorphic rock will have maybe 1 or 2 parts per billion of gold in it. Some volcanic rocks, very iron magnesium rich volcanic rocks, of which there are some deep in the crust in Victoria, may have up to 4 or 5 parts per billion. What we need to do basically is extract 1 or 2 parts per billion of gold out of that rock using the very large volume of fluid as a transporter.
Can you tell me exactly how the hydrothermal fluid is stored within the rock in these reservoirs at depth?
Okay, the interesting point there is unless the rock is being actively deformed, it has very little capacity to store fluid, that is, it has very little porosity in it. when the rock is actively deforming, and this is a very important concept which we came across some years ago, is that if the rock is not deforming, no storage capacity. If we want fluids to be stored in a rock and migrate through a rock, we need to actively deform that rock, because deformation creates the porosity, the storage capacity for containing those fluids. Deformation also allows the pores and fractures to connect up and actually allows the fluid to migrate through the rock. If the fluid was being generated by metamorphism deep in the crust, but the crust was not also deforming, you'd probably have very dispersed fluid flow out of the crust. But as the crust is deforming, and often we find that the deformation localises into narrow domains of high deformation rate. That's where the fluid tends to be drawn into those structures and then migrates to shallower crustal levels.
Okay, well this is a point I want to clarify. In the deeper areas where these microfracturing processes are happening, do we have a more dispersed reservoir before we're getting up into the shear zones?
Yeah, we must have a dispersed reservoir because the gold is distributed at the grain scale through this very large volume of crust. And so the trick is, how do we get the gold from those individual grain scale, and we're talking here of grains which are less than a millimetre in diameter, over a very large volume of crust. We've got to get that fluid into channelways. So it's very much like the river tributary system. There's got to be a lot of distributed microcracks over a very large volume of crust. And those microcracks, which have dimensions of maybe a few millimetres long by maybe a few tens of microns wide, they form the pathway and the storage. But the fluid's going to go nowhere unless they can actually bleed their fluid or drain their fluid into some sort of bigger structure which is very permeable or has a very high capacity for fluid transport.
Well, given that we've got all these structures, what is it that actually forces the fluid to rise?
That's a good question. The thing to think of is that when you're very deep in the crust, say think of being 15 kilometres deep, the rock above you is creating enormous pressure. So these fluids are highly pressurised. Think of fluid at a shallow level in the crust. The fluid there is not very pressurised, is it? It's much less pressurised. So it's that gradient in fluid pressure from deep in the crust to shallow in the crust which drives the fluid flow. It's just the same way you apply a pump to a tyre. You generate a high pressure in the pump and you push that air into the tyre. The crust is doing the same thing. It's squeezing and pressurising the fluid, squeezing it to higher levels in the crust.
So that's implying pretty large-scale geological processes, and you've got very large plate movements causing metamorphism.
That's right. So while the rocks are being metamorphosed or cooked up, they're also deforming. So we're producing these great big fold systems and big fault zones are developing. The whole period of crustal shortening during the gold formation in central Victoria probably occurred in less than 10 million years. What we do know, although vein systems were forming throughout that folding history, many of the gold deposits formed very late in that history. So the gold cuts across the folds and is actively forming when some of the faults are cutting across those folds. So from that we could judge that probably big deposit systems such as Bendigo might have taken less than 1 million years to form.
So what volume of source rock do you think would be required to provide the gold for somewhere, say, like Bendigo?
Okay, that's a fairly straightforward sum. If we look at the gold budget in Bendigo, and we've got a known resource of 500 or 600 tonnes, and maybe there's a fair bit more than that which is deeper. To produce a Bendigo, you need a volume of crust which would measure something like 30 kilometres by 30 kilometres in area, and maybe about 5 kilometres deep. So there's plenty of space in the mid to deep crust in Victoria to produce that sort of system. And it's intriguing if you do that mass balance calculation. We want this area 30 by 30. It's quite interesting that the deposit systems, the big deposits like Ballarat, Bendigo, Castlemaine, various others, have a separation of about 20 to 30 kilometres, maybe 40 kilometres at most. And that's consistent with needing to scavenge this fluid and gold from that crustal volume.